My dear students, welcome back to our channel. In this video, I will be explaining the BCA third semester subject database design as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 5 first important short question is transactions with example. A transaction in a database is a group of operations that are treated as a single unit of work. Either all operations succeed or none do. This ensures the database stays correct and consistent. Key properties ACID. 1. Atomicity, all or nothing. 2. Consistency, database remains valid. 3. Isolation, transactions don't interfere. 4. Durability, changes are permanent. Example. Consider a bank transfer. Elise wants to transfer 100 rupee to Bob. Transaction steps. 1. Deduct 100 rupees from Elise's account. 2. Add 100 rupee to Bob's account. Scenario 1. If step 2 fails, atomicity ensures step 1 is rolled back, so Elise doesn't lose money. Scenario 2. Multiple transfers happen at the same time. Isolation ensures balances are correct despite concurrent transactions. In simple words, think of a transaction like a safety-locked parcel. You can't deliver only half the items. Either the whole parcel reaches safely, success, or nothing is delivered, rollback. Transactions make databases safe, reliable, and trustworthy, especially in banks, e-commerce, or ticket booking systems, where errors can cause serious problems. Next important short question is 2. Two-phase locking to PL with example. Two-phase locking to PL is a concurrency control method used in databases to ensure transactions execute safely without interfering with each other. It prevents problems like lost updates or inconsistent data. How PL works? A transaction goes through two phases. 1. Growing phase. Transaction acquires all the locks it needs, shared or exclusive. No locks are released during this phase. 2. Shrinking phase. Transaction releases locks after its operations. No new locks can be acquired in this phase. Example. Transaction T1 updates Elise's bank account. Transaction T2 reads Elise's balance. Without PL, T1 and T2 may interfere. T2 reads wrong balance. With PL, T1 locks Elise's account for update. T2 must wait until T1 finishes balance is correct. In simple words, think of PL like taking a ticket and holding a pen while updating a record. Growing phase, pick up all pens you need to write locks. Shrinking phase, put pens down after finishing, release locks. PL ensures database transactions are safe and consistent, even when many people are using it at the same time, like in banking or online shopping systems. Next important short question is 3. Serializability with example. Serializability is a concept in databases that ensures transactions executed concurrently give the same result as if they were executed one after another, serially. It is a key idea for concurrency control, keeping the database consistent. Why it's important? When multiple transactions run at the same time, their operations can interleave, leading to incorrect results. Serializability guarantees that even with interleaving, the final database state is safe and correct. Example. Transaction T1, Elise transfers 100 rupee to Bob. Transaction T2, Bob withdraws 50 rupees. Without control, T2 might read Bob's balance before T1 updates it, causing errors. With serializability, the database ensures the effect is the same as if T1 and T2 ran one after the other, avoiding inconsistencies. In simple words, think of serializability like two chefs sharing one kitchen. Even if they cook at the same time, the final dishes taste exactly as if each cooked alone. Serializability is like a safety rule for concurrent transactions, making sure your database behaves predictably and correctly, just like a well-organized kitchen. Next important short question is 4. Recoverability with example. Recoverability in databases ensures that if a transaction fails, the database can recover to a consistent state without losing correct data. It is a key part of transaction management and prevents errors from propagating. Why it's important? When multiple transactions run together, one may fail after partially updating the database. Recoverability ensures that any dependent transactions are rolled back or handled correctly to maintain consistency. Example: Transaction T1, transfer 100 rupees from Alice to Bob. Transaction T2, calculate Bob's total balance for a report. Scenario: T1 fails after deducting money from Alice but before adding to Bob. Recoverable system: T2 waits or rolls back, database is corrected, no money is lost. In simple words, recoverability is like having a safety net while juggling. If one ball drops, transaction fails, you can pick it up and continue without breaking the performance. It makes databases reliable, especially in banks, e-commerce, or ticket booking systems, where failures can happen but data must remain safe and correct. Next important short question is 5. Give an overview of lock management. Overview of lock management with example. Lock management is a technique used in databases to control access to data when multiple transactions run at the same time. It ensures consistency, isolation, and prevents conflicts like lost updates or dirty reads. How locks work? A lock is a mechanism that prevents other transactions from accessing the same data simultaneously. Types of locks. 1. Shared lock. S-lock allows multiple transactions to read data but not write. 2. Exclusive lock. X-lock allows one transaction to read and write, blocking others. Example: Transaction T1 wants to update Alice's balance. Transaction T2 wants to read Alice's balance. Lock management. T1 places an exclusive lock on Alice's record. T2 must wait. Once T1 finishes and releases the lock, T2 can read safely. In simple words, think of a library book. Shared lock is equal to multiple students can read the book. Exclusive lock is equal to one student writes notes in the book, others must wait. Lock management ensures safe, conflict-free access to data in banks, online shopping, or ticket systems, keeping the database accurate and reliable even when many users work at the same time. Next, Unit 5. Long questions. First important long question is 1. ACID properties in database transactions. In database systems, transactions are units of work that must be executed reliably. To ensure this, every transaction follows the ACID properties, which make the database safe, consistent, and trustworthy, even when multiple users access it simultaneously. 1. Atomicity, all or nothing, ensures that a transaction is treated as a single indivisible unit. Either all operations succeed or none do. Example: Alice transfers 500 rupees to Bob. Steps: deduct 500 rupees from Alice, add 500 rupees to Bob. If the second step fails, the first is rolled back, ensuring alias doesn't lose money. 2. Consistency, keep database valid. Ensures that database rules and constraints are not violated. Each transaction moves the database from one valid state to another. Example: total money in all bank accounts remains the same after a transfer. 3. Isolation, transactions don't interfere. Ensures transactions execute independently, even if they run concurrently. Example: Alice and Bob withdraw money at the same time. Isolation ensures both transactions see a consistent view of balances, avoiding conflicts. 4. Durability, permanent changes. Ensures that once a transaction is committed, changes are permanent, even if the system crashes. Example: after Alice transfers 500 rupee to Bob and the transaction commits, the database remembers it permanently, even if power fails immediately afterward. In simple words, think of ACID like a bank safety system. Atomicity, either the whole transfer happens or nothing happens. Consistency, money doesn't disappear or appear magically. Isolation, everyone's transactions happen in a controlled, separate manner. Durability, once done, it cannot be undone by a crash. Why ACID matters? ACID properties are essential for banking systems, e-commerce, ticket booking, and other real-time applications where errors can cause financial loss or data corruption. They make transactions reliable, predictable, and safe, giving users trust in the database system. This combination of safety, accuracy, and reliability is why ACID is considered the cornerstone of transaction management in databases. Next important long question is: 2. Schedules in database transactions. In databases, when multiple transactions execute at the same time, their operations may interleave. The order in which these operations are executed is called a schedule. Proper scheduling ensures the database remains consistent and correct, even with concurrent transactions. Types of schedules. 1. Serial schedule. Transactions are executed one after the other without overlapping. Simple and safe but can be slow. Example: T1, transfer 100 rupees from Alice to Bob. T2, check Bob's balance. Here, T2 starts only after T1 completes. 2. Non-serial schedule. Transactions interleave, operations of T1 and T2 happen simultaneously. Faster but can cause conflicts if not managed properly. Example: T1 deducts 100 rupees from Alice. T2 reads Bob's balance. Without control, T2 may see an incorrect value. Conflict and view serializability. Conflict serializable. A non-serial schedule is equivalent to some serial schedule if conflicting operations are reordered safely. View serializable. Even if operations are interleaved, the final result of the database is the same as some serial execution. Example: transactions T1 and T2. T1, update Alice 100 rupees, update Bob 100 rupees. T2, read Bob's balance, read Alice's balance. Schedule is non-serial, but using locks or 2PL, the database ensures the result is as if T1 ran fully before T2, maintaining consistency. In simple words, think of schedules like students using one computer lab. Serial schedule: one student finishes before the next starts, safe but slow. Non-serial schedule: students work at the same time, faster, but must take turns on the same machine, locks, to avoid mistakes. Why schedules matter? Proper scheduling ensures no lost updates, consistent database state, correct results even with many users working concurrently, In short, schedules are like traffic rules for transactions, allowing multiple transactions to run efficiently and safely without crashing the system or corrupting data. Next important long question is 3. Concurrent execution of transactions. In databases, multiple transactions often run at the same time to improve performance and save time. This is called concurrent execution. While it increases efficiency, it can also cause problems like inconsistencies, lost updates, or dirty reads if not managed carefully. Why concurrent execution is used? Faster response. Multiple users can access and update the database simultaneously. Better resource utilization. CPU and memory are used efficiently. Real-life example. In online banking, many people check balances, transfer money, or pay bills at the same time. Challenges. When transactions overlap, issues can occur. 1. Lost update. 2 transactions update the same data, and 1 update is lost. 2. Dirty read. A transaction reads data that is not yet committed by another transaction. 3. Inconsistent retrieval. Reading some old values and some new values, leading to wrong results. Example. Transaction T1, transfer 500 rupees from Alice to Bob. Transaction T2, check Alice's balance. Concurrent execution without control. T2 may read Alice's balance before T1 finishes, showing incorrect balance. Solution. Use concurrency control techniques like locks to lock Alice's account while T1 updates it. Timestamps. Transactions executed based on their order of arrival. Serializability. Ensure the effect is the same as if transactions ran one after another. In simple words, think of concurrent execution like multiple people writing on a shared notebook. If everyone writes without rules, pages get messy, lost updates, wrong data. If they follow rules, locks, orderly turns, everyone can write safely and efficiently. Benefits. Efficient system performance. Reduced waiting time for users. Safe and consistent data when concurrency control is applied. In short, concurrent execution is like a busy railway station. Many trains, transactions, move at the same time, but signals and rules, concurrency control, ensure everything runs smoothly without accidents, keeping the database accurate and reliable. Next important long question is 4. Lock-based concurrency control. In databases, when multiple transactions run at the same time, they may try to access or update the same data. This can cause conflicts, inconsistencies, or lost updates. To prevent this, we use lock-based concurrency control, which ensures safe and orderly access to data. How it works. A lock is like a reservation on a data item. Only transactions holding the lock can access or modify that data. Other transactions must wait until the lock is released. Types of locks. 1. Shared lock, S-lock. Used for reading data. Multiple transactions can read the same data at the same time. Example, 2 students can read the same book. 2. Exclusive lock, X-lock. Used for writing updating data. Only one transaction can hold it at a time, others must wait. Example, one student writes notes in a book, others cannot write until done. Two-phase locking, 2PL. Transactions follow 2 phases. 1. Growing phase, acquire all locks needed. 2. Shrinking phase, release locks after operations. Ensures that transactions are serializable, safe as if run one by one. Example. Transaction T1, transfer 500 rupees from Alice to Bob. Transaction T2, check Bob's balance. Without locks, T2 may read balance before T1 finishes, causing wrong results. With locks, T1 places exclusive lock on Ali's and Bob's accounts. T2 waits until T1 completes and releases locks. Data stays consistent and correct. Advantages: prevents lost updates and dirty reads. Ensures serializability. Supports safe concurrent access. In simple words, think of locks like traffic signals at intersections. Green light is equal to transaction can proceed. Red light is equal to wait until safe. Locks manage the flow of transactions so no crashes or data conflicts occur. Lock-based concurrency control is essential in banking, e-commerce, online ticket booking, or any system with multiple users, keeping the database accurate, consistent, and reliable while allowing multiple operations to happen at the same time. Next important long question is 5. Dealing with deadlock in databases. In databases, a deadlock occurs when two or more transactions wait indefinitely for resources, like data locks, held by each other. This can freeze operations, causing delays and inconsistencies if not handled properly. Example of deadlock. Transaction T1 locks Ali's account to transfer money to Bob. Transaction T2 locks Bob's account to check balance. Now T1 wants to lock Bob's account and T2 wants to lock Ali's account. Both are waiting for the other to release the lock deadlock. Ways to deal with deadlocks. 1. Deadlock prevention. Design the system to avoid cycles of waiting. Example, always acquire locks in a fixed order. Example, always lock Ali's account before Bob's. Pros, prevents deadlocks entirely. Cons, can reduce concurrency. 2. Deadlock detection and recovery. System monitors transactions to detect cycles. When a deadlock is found, it chooses a victim transaction to roll back. Example, roll back T2 allowing T1 to complete, then restart T2. Pros, maximizes concurrency. Cons, slight overhead for monitoring. 3. Timeout method. Transactions wait for a certain time to acquire a lock. If the lock is not acquired in time, the transaction is rolled back and retried. Simple and widely used in practice. In simple words, think of a deadlock like two cars stuck at a narrow bridge from opposite sides. Both wait for the other to move, so no one can pass. Solutions. Prevention, only one car can enter first. Detection, spot the blockage and reverse one car. Timeout, if waiting too long, one car backs up automatically. Why deadlock handling matters. Deadlocks can stop the system, cause transaction failures, and affect user trust. By using prevention, detection, or timeout methods, databases ensure smooth, safe, and efficient operations even when many users access the system concurrently. In short, dealing with deadlocks is like traffic management in a busy city. Rules, monitoring, and backup plans keep the flow smooth and prevent jams, ensuring all transactions complete correctly.